In this presentation, we're going to explore magnetism a little further, and we're going to look at the magnetic field due to a bar magnet. We're going to look at how the strength changes. We're also going to look at the fact that a current-carrying wire can produce its own magnetic field. So we're going to look at the PhET simulation, that is magnetism, magnetic field, and electromagnets. This particular PhET simulation is a Java file, so a lot of computers do not like to run Java files. So that's why we're going to do this sort of in the presentation. So I'm going to go ahead and open up the simulation. I'm going to click on the show the field meter for this particular bar magnet. I'm going to move the meter around, and I'm going to take notice of where the magnetic field strength, how it changes. Where is it the strongest? Where is it the weakest? And I'm also going to look inside the magnet, see if there's a magnetic field there, what does it look like, and so on. So I have that simulation ready to go. So here's our bar magnet, and here's our compass. This is similar to what we looked at before. So I'm going to go ahead and remove the compass. We really don't need that there. I'm going to hit or click on the show field meter. So there's a number of different pieces of information here, and I don't really care about BX, BY, or this angle right here. So what those are telling me is the strength of the magnetic field that points along the different directions, what points along the horizontal, the vertical, and then what angle those make with respect to one another. So in other words, what angle does the compass make? I want to focus on this number right here, which is the actual strength of the magnetic field, the very top one. And the magnetic field here is being measured in what are called Gauss. So as I move this around, we can take note of what happens to the magnetic field strength. And the first thing you should realize is that as you get closer and closer to the pole of the magnet, that magnetic field strength gets larger and larger, right? So the magnetic field strength really close to this particular bar magnet, but not inside, haven't got quite inside yet, is very strong, right? So it's around 90, and as I move away from the magnetic field strength decreases, right? Until I'm pretty far away, it's almost non-existent. And then if I go up, the magnetic field strength also decreases as I go farther away. And even when I'm close, to the magnet, but not near one of the poles, the magnetic field strength is pretty small. If I get over to the North Pole and I get closer and closer, there we go, the magnetic field strength is also getting to be very large there. So we see the strongest magnetic field near the poles, and it gets weaker the further away that you get. If I want to look inside the magnet as we did before, I realize that there is a magnetic field inside the bar magnet, and that it's pretty straight going through there. Let's use the field meter to see what the strength of that magnetic field is inside the magnet. And what I see is that the magnetic field strength is pretty big inside the magnet, and if I could hold this steady and go across, one of the things, let's see if I could hold it here, that I would realize is that it stays about the same value. It's not too far off. If I could just hold it steady as I go all the way across. So it's a relatively uniform magnetic field as I'm going across inside the magnet, and it's actually the strongest inside the magnet. And then as you get to the poles, it's still pretty strong, but as you move away from the magnet, it gets smaller. So the strongest magnetic field is actually inside the magnet itself. And then if you're talking about outside the magnetic field strength is strongest near the poles and decreases as you get further away. So we answered this next question. If I move the magnetic field meter over the magnet, what happens to the strength of the magnetic field inside the magnet as compared to around the magnet? It's definitely very strong inside the magnet, very strong magnetic field. The next thing we're going to do is we're going to click on Show Planet Earth, and we're going to see what happens when we look at that. And let's take note of where the north magnetic pole is of the bar magnet that appears to be like the Earth's magnet. So we have our bar magnet, and we're going to go ahead and we are going to click on Show Planet Earth. And we don't need to have our magnetic field meter anymore. And so one of the things that you should notice is that the Earth has a magnetic field, and so I can see the compasses around the Earth that are pointing in different directions, so there is a magnetic field that's present. And one of the things that you should notice about the Earth's magnetic field is that the field lines, or those arrows from the compasses, look like a bar magnet. So the Earth's magnetic field is actually behaving very similar to a bar magnet, with a south magnetic pole that is located near geographic north, and with a north magnetic pole that is located near geographic south. There is not actually a bar magnet in the center of the Earth, but it appears, or it behaves, as if there is a bar magnet in there in terms of what the magnetic field looks like. So here's another representation of the Earth with its magnetic field. Here's a three-dimensional picture with the magnetic field lines, and so the magnetic field actually points from geographic south and goes around, and if I put compasses around the Earth, I would see these deflections of the compasses. But it's really important to realize that the magnetic north pole is actually located at the geographic south pole. So geographic south, of course, is down here, and that's magnetic north, and obviously vice versa. The Earth's magnetic field strength is actually relatively weak. So if we took a compass out and we were walking around with the compass, we could definitely experience a force on that compass that would tell us the direction of the Earth's magnetic field. However, if we brought another stronger magnet, or just a magnet nearby that compass, the compass would actually be deflected by that magnet. So the Earth's magnetic field is relatively weak in terms of other just permanent magnets. So where do you think the Earth's magnetic field actually comes from? So obviously there's not an actual bar magnet in the center of the Earth, but it's believed that the Earth's magnetic field is actually coming from magma, or like a lava. So the core of the Earth is not solid, it's actually in liquid form, and there's some iron in there, and iron is a magnetic material, and that material is probably moving in the Earth's around with the Earth, and that is what is believed to be producing the Earth's magnetic field. Now, the other, just some general comments about the Earth's magnetic field. The magnetic north, I'm pointing to south, so magnetic south pole of the Earth over here is actually not directly under geographic north. So they're actually tilted slightly, and is called the angle of declination. So there's a slight angle between geographic north and magnetic south, and that changes over time. I think the angle is pretty small. It might go up to 11 degrees, but it does vary over time. And so that's something that scientists and people who use the Earth's magnetic field to tell direction actually have to consider as they are using those fields to determine direction. The other thing to keep in mind is that the Earth's magnetic field actually has reversed over time, and we're talking about long periods of time. And this is known because if you look at magma that has come out, and you look on, I think they find it on the ocean floors, you can see that the domains of the magma that has become solidified has actually changed over time. So it turns out that permanent magnets are not the only things that can actually produce magnetic fields. Electric current can actually also produce a magnetic field. And if I look at a straight current carrying wire, and I look at the direction of the conventional current, so this would be the movement of positive charge if we thought about conventional current, then the magnetic field for a straight current carrying wire makes concentric circles around that straight wire. This was kind of discovered by accident. I forget the exact time frame of when this was discovered, but essentially during the study of electricity, a scientist had a compass nearby a current carrying wire and noticed that it was deflected when the current was on. One of the ways that we can tell the direction that the magnetic field strength will point, or the magnetic field will point, is by using something called the right-hand rule. If you put your thumb in the direction of, or you grab onto the wire, put your thumb in the direction of the current, the way that your fingers would wrap around the wire, keeping your thumb in the direction of the current, is the direction that the magnetic field would point for a straight current carrying wire. If I change the direction of the current to be in the opposite direction, then the direction of the magnetic field strength would be in the opposite direction. And we could tell this by taking a compass and putting it around that current carrying wire. So we can also form wires into different shapes. And if I put a current carrying wire into a loop, so here is a circular loop here, I get a magnetic field strength that looks very similar to the magnetic field of a bar magnet, where you have the magnetic field leaving the top, let's say, portion of this loop, and then sort of bending around and coming back through. As I add additional loops, the magnetic field strength actually increases. So here's a picture over here where I have lots of loops of wire, and in the center of those loops, the magnetic field is pretty straight, just like a bar magnet. And at the end, it appears that the magnetic field is pointing straight, but then curves back around to the south. And so this looks just like a bar magnet. This is called a solenoid, and a solenoid is essentially an electromagnet. And of course, here's the same type of picture of just the bar magnet. And if I look at the lines, the magnetic field lines look very similar to one another. So for a solenoid, you're going to have multiple turns, and these are used often in, I mentioned this before, but like a junkyard magnet, right? Something you can turn on and off, so you can have a very strong magnetic field when you run current through it, but then you can also turn off the current and then the magnetic field goes away. So it turns out that the strength of a magnetic field for a current carrying wire depends on a couple of things. It's proportional to the amount of current that's flowing through the wire, the amps. So if you increase the current in the wire, the magnetic field strength goes up. If you turn the current completely off, the magnetic field disappears. It's also indirectly proportional to the distance that you are away from the wire. So if you're close to the wire, the magnetic field strength is larger, and as you move further and further away, the magnetic field strength decreases. So that's that inverse relationship. As the distance gets bigger from the wire, the magnetic field decreases. And we use B to represent magnetic field strength. So what we're going to do is we're going to look again at one of those PhET simulations, and we're going to look at answering a couple of questions. So at the top left-hand corner of our simulation, we're going to click on electromagnet, and we're going to see a battery that's connected to a wire, and then we're going to also have a magnetic field that's represented by the compasses. We're going to click on show the magnetic field meter, and then we're going to move the meter around inside the coil of wires. We're going to see where is the magnetic field the strongest, and what do we notice about the field as you move inside the coils? Does it stay relatively constant? So I'm going to click on electromagnet. Here's my battery. This is DC, so I have current that's going through here. This is the electron current. I'm going to take, and I can move my compass around. I can see that there's definitely a magnetic field there. I'm going to go ahead and I'm going to click on show field meter, and again, I only care about that first number, which is the strength of the magnetic field. And let's see what happens as I get closer to the coils. The magnetic field strength is getting very strong as I get closer and closer to those coils, and as I get further and further away, the magnetic field strength decreases. I'm going to take the meter now and I'm going to move it inside the coils, and let's look at what the strength of the magnetic field is. So when I'm inside the coils, it doesn't seem to matter where I move this, the magnetic field is constant. So having these coils, these circular coils with current running through them, produces a uniform, constant magnetic field inside of the coils. All right, so we're going to place the field meter so that it's measuring the field inside the coils, and we're going to change the number of coils from 3 to 2 to 1, and let's see what happens as the number of coils decreases, what happens to the magnetic field strength. So I'm going to put this inside, and right now the magnetic field strength is 300, and there are 4 loops. I'm going to change it to 3, and we can see what happened to the magnetic field. It decreased. I'm going to change it to 2. The magnetic field decreased even more, and I'm going to change it to 1, and the magnetic field is the smallest, right? So as I increase the number of turns of coil, the magnetic field strength gets bigger and bigger, and as I decrease the number of turns, the magnetic field strength decreases. I'm going to keep that field meter in place, and I'm going to change the number of coils back to 4, and I'm going to adjust the voltage in the battery from 8 to 6 to 4 to 2 to 0, and I'm going to see what happens to the magnetic field strength and why does this happen, and we're going to look at the charges as they move, and then we're going to also change the polarity. So we're going to continue to do this and then change the polarity and see what happens to the magnetic fields as we do that. Okay, so I'm keeping the number of turns the same. Here's my voltage. It's at 10 volts. Let's take note of how these electrons are moving and see what happens to the magnetic field as I decrease the voltage. So I'm decreasing it to 8. The magnetic field inside there was 300. Now it's 240, and those electrons are not moving as fast. I'm going to move it to 6. They're slowing down even more, so less current. Magnetic field is even smaller. Changing it to 4. Magnetic field is even smaller. Electrons are moving slower. 2. So electrons are hardly moving at all. The magnetic field strength is decreasing. And when the current is 0, there's no current in the circuit. If there's no current, then there's no magnetic field. Now I'm going to go back and put it over here at 9, and I want everyone to take notice of the compasses and the direction that they're pointing. So all of the north ends of the compass inside are pointing to the right, and the south are pointing to the left. Look at what happens to the magnetic field as I change the polarity of the battery. So the strength of the magnetic field is still the same, so I'll put this all the way back to 10 and it's 300, but the polarity of the magnetic field has switched so that now the north end of these compasses are pointing to the left and the south end of the compasses are pointing to the right. So we can watch it change as I do this. See, they flip, 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 flip. So changing the direction of the current switches the direction of the magnetic field. All right, I'm going to keep the magnetic field meter in place and click on the AC source, and an oscilloscope is going to appear that shows the voltage changing in time. What do we notice about the magnetic field? And then we can also change the speed of the AC oscillation, and we can see what happens there. So here's our picture here, and now we're going to click on AC. And what we notice is that the current that's going through that wire is now fluctuating. It's oscillating back and forth. Those electrons, current direction is changing direction. And as that happens, the magnetic field strength increases and decreases, increases and decreases. But not only that, if you check on the compasses, they are switching direction back and forth. And we can change the strength of that AC source. It's a stronger current now that's oscillating, and I get a stronger magnetic field that's changing. And I can change how it oscillates. So now it's a slower oscillation. It's still changing, but it's just changing slower in terms of direction being one direction and then the other direction. And the polarity is actually switching here for these magnetic fields. So there's the north end, now it's the south, right here, north, and then south. So we've learned that a permanent magnet can create a magnetic field, but also an electromagnet, current-carrying wire, can also produce a magnetic field. And that magnetic field strength depends on a lot of things. It depends on how many turns of coil you have. It depends on the strength of the current that's going through there. If you have a bigger current in the wire, you're going to have a stronger magnetic field, and so on.